Um, this is a question about refractive index. A student measures the refractive index of a glass of microscope slide. And the question will give you the instructions that will be followed through the through this experiment. Use traveling microscope to determine position x1 of a mark on a sheet of paper. He then places a slide over the mark and find the position x2 of the image when viewed through the slide. Finally, he uses the microscope to determine the position x3 of the top of the slide. Like this, no matter the way that he did this experiment, because we are not concerned about anything about the carrying out the experiment. We are focusing only about presenting data, finding uncertainty, these things only. We are given this table x1, x2, x3. We are given the formula also that he used, x3 minus x1 over x3 minus x2. Determine the refractive index of the glass by correct number of significant figures, ignoring any uncertainty. Right? Any uncertainty. Okay, first part, guys, the aim of this part of question only to examine you how you will deal with significant figures. Okay, but be careful. It's just direct calculation. Refractive index equals x3 1.35 minus x1, which is 0.20 over x3 1.35 minus 0.59. In addition or subtraction, I have to focus on the number of decimal places. So this becomes 1.15, right, over 0.76, which is equivalent to 1.5131. This is what I got. On the calculator, using the calculator. I can't keep it as it is because I have to write it to the similar number of significant figures. So it's only 1.5. Two significant figures. Why two significant figures? Because here two significant figures, here three significant figures. These type of questions, guys, pay attention to these type of questions, because this type of questions focus on the number of significant figures, dealing with number of significant figures, because I don't believe that they ask you only to do this calculation, which is something easy, can be done through the calculator. Now, this is part one. In part two, we are asked about the uncertainty. Okay. Now here we have addition and multiplication in this type of question. We have addition of the uncertainty and multiplication. So first of all, I have to find the uncertainty in x3 minus x1 and the uncertainty in x3 minus x2. Then I have to add their fractional uncertainty. For addition, no matter for subtraction, I have only to add their uncertainties. 0.02 plus 0.02, which is 0.04. This is as well 0.02 plus 0.02, so this is what 0.04. This is if we have this is the uncertainty for addition. Now let's do the uncertainty for division. Delta n over n equals delta x3 minus x1 over x3 minus x1 plus delta x3 minus x2 over x3 minus x2. I think you remember this. This is our fractional uncertainty. Now we are asked about delta n over 1.5 equals. This is 0.04 x3. This is x3 minus x1, right? So 0.05 over 1.15 plus, there is no any power here, x. This is also x3 minus x2, which is 0.75, 0.04 over 0.6. So delta n, after doing this calculation, this part is 0.88. Sorry, 0.088. So this becomes times 1.5. So here we will get 0.0 or 0.1. So n eventually equals 1.5 plus minus 0.1. Again, guys, here, one decimal place, one significant figures, right? This is actually the condition, or these are the conditions for writing the uncertainty. After the experiment, the student finds that traveling microscope is badly adjusted so that the measurement of each position is too large by, focus on this, is too large by fixed value, 0.05. What does this mean? This means, guys, that there's a shift in all readings, right? There is a shift in all readings by 0.05. What is the type of this error? It's a systematic error, right? This is what? Systematic error. Why this is a systematic error? Because there is a constant shift in all readings. Outline the effect that the error in B will have on the calculated value of the refractive index of the glass. Actually, I may check this. N equals this systematic error, must be what? Must be subtracted, let's say, okay, from the readings. So this becomes, be careful, 1.35 minus 0.05 the systematic error minus 0.02, sorry, 0.2. Minus 0.05 over 1.35 minus 0.05 minus 0.59 minus 0.05, right? This must be subtracted. This is like a zero error. Must be subtracted from all readings. What can we observe here? That these values eventually will be cancelled out from each from numerator and denominator. So eventually the value of n does not change, right? Y does not change because the values of numerator and denominator do not change. Okay. After correcting the adjustment of the traveling microscope, the student repeats the experiment using glass of 10 block of 10 times thicker than the original microscope slide. Explain the change, if any, to the calculated result for the refractive index and its uncertainty. Guys, this is exactly similar to the question of measuring a period of oscillation, right? If I repeat, if I measure the time for several oscillations, I will have eventually less absolute uncertainty. If I measure the thickness for single slide, microscope slide, or for 10 times thicker, actually 10 times thicker will increase measured value, but the absolute uncertainty stays the same, so the fractional uncertainty will be less. Okay. Yeah. For example, guys, if I want to measure x3, okay, x3 will be 10 times larger, right? Yani, let's say it's prime, so it's 10 times x3, the original one. X1 will be 10 times the new one, 10 times the previous one of the high. X2, the new one, is 10 times what? X2. So eventually refractive index does not change because it seems that I multiplied the numerator by 10 with denominator by 10. No any changes. But if I measure the absolute uncertainty here for this part, the absolute uncertainty, the fractional uncertainty. The absolute uncertainty does not change, but it will be over 10 times of x3. Okay, because this uncertainty depends on the tool itself, right? The tool 0.02, this is let's say the smallest division of our tool, divided by measured value, so the fractional uncertainty will be less, right? The fractional uncertainty will be less for x3, for x1, for x2 as well. So as a refractive index, it does not change because, as what I mentioned before, it seems that I multiplied both numerator and denominator by 10, but the fractional uncertainty will be less. Okay. Another question. Student, an experiment is undertaken to investigate the relationship between temperature of the ball and the height of the first bounce. A ball is placed in the beaker. Water enters the ball and water are the same temperature. The ball is released from height 1 meter above the bench. The maximum vertical height from the bottom of the ball above the bench is measured first bounce. This procedure is repeated twice and an average H is calculated from 3 measurements. We're given H T. Student hypothesis states that H is proportional to T square. Using 2 points on your line of best fit, whether or not is valid hypothesis.
But before this, I have to draw the best fit. So I have to select 2 points on the best fit. Be careful. I have to select 2 points on my best fit to check these, to check if they are constant, or if the ratio between h and t squared is constant or not. So I have to select two sets of data, this one, and this one. Okay. These also sets of data lie on the best fit. Okay, so be careful. You have to draw first of all a best fit, then select 2 points that lie at the best fit, like what I did here.
If you remember, to have something directly proportional, this means that H over T square for any point or any set of data على الgraph should be constant in order to be (65). The second point over 80 squared. These two sets of data of point. Now, if I want to judge if these values are constant or not, or could be constant, here, guys, difference between these two values can be either real difference, so if it's a real difference, these values are not constant. Let's say this is K1 and this is K2, or there is not real difference. This difference is caused by uncertainty. How can I distinguish between these two things? Here I have to find something called percentage difference. Percentage difference, it's the difference between these values over the average of these values. Times 100%. If this percentage difference greater than maximum uncertainty or percentage uncertainty, this is a real difference. If this difference is less than the maximum percentage uncertainty, this is not a real difference. The values are constant, right? But this difference is caused by uncertainty, right? Here, the values are constant. And what does this mean, guys? And let's say if I can do the experiment without any uncertainty or any error, these values will be the same, exactly the same. But this difference between these two values is a result of uncertainty. So if this percentage difference is less than the maximum percentage uncertainty, the values will be considered as constant value. Now let's apply these. Now let's take percentage difference. Percentage difference, okay, which is 0.000187 minus 0.000694 as an absolute value over 0.000187 plus over 2. This is the average times 100%. Okay, guys, here we found as you see, I selected two sets of points. I found from the graph, found K1 and K2, which must be a constant if the theory is valid. Now I have two different values. Basically, if I would like to judge if they are constant or not, I have to use this. And actually here we have two, or the difference can be caused by two things. Either it's a real difference, this means that the suggestion or the theory is not valid. The two values are not constant, right? Or they are almost constant. Yani, they should be constant, but as a result of uncertainty, there is a difference. How can I check this? If I want to check this, I have to calculate something called percentage difference. Percentage difference between these two values is the difference between these two values over the average of these values times 100% of an absolute value. If this percentage difference is greater than the maximum percentage difference or maximum percentage uncertainty, so this is a real difference. This is beyond the limit of experimental accuracy, beyond the limit of experimental accuracy, this difference. Now, if the percentage difference is less than the maximum percentage uncertainty of these 2 points, so this is within the limit of experimental accuracy. And this difference is not beyond the limit of experimental accuracy. It's within the limit of experimental accuracy, within the limit. So the values are constant. In other words, guys, if I can do this without any mistakes, without any errors, without any uncertainties, these values would be constant, exactly the same. Now, I did this calculation. The percentage difference is equivalent to difference between them over the average, I get 142%. It's very obvious that uh, these two values are beyond the limit of experimental accuracy. Now, for practice, I have to find the largest uncertainty for my selection of the 2 points. This is the first point, this is the second point. This is obvious that this is has the largest uncertainty. These two values, 0.625, this is approximately 0.6215, so the uncertainty is 0.01, right? Approximately. For practice only, if I calculate the largest uncertainty or percentage uncertainty, the largest one, 0.02 over 0.625 times 100%, definitely it will be less than the percentage uncertainty. Less than the percentage. So what can I write as a conclusion? Because this has a mark. Percentage difference is greater than percentage uncertainty. So the values are beyond the limit of experimental accuracy. So um, the theory is not valid. Okay.